Alright, welcome to Chapter 15, portion on solubility. Our first video here, 15.8 of Chapter 15, will be on solubility. Be able to calculate the solubility product, which is called KSP, and vice versa, be able to calculate the solubility if you know what KSP is, so between those two things. And then lastly, to predict the relative solubility from KSP values. Alright, so this section really focuses on what we used to call insoluble solids that formed during a precipitation reaction. Insoluble solids turn out they're actually slightly soluble. They're not very soluble, but they do have some solubility characteristics to them. These substances, when they do become soluble, they establish dynamic equilibrium between the precipitate and the soluble cations and the soluble anions. So for example, if we do a solution reaction with sodium chloride and silver nitrate, it looks something like this. Sodium chloride solution is aqueous. It reacts with silver nitrate, which is aqueous. And then the products of this reaction is double replacement, and we get AgCl, and we get sodium nitrate, like so. And using our solubility rules, we know that sodiums and nitrates are always soluble, so this is soluble. And then chlorides are usually soluble unless they're with silver, mercury, or lead. And here's silver, so this is the solid precipitate. So this is the precipitate we form, and we usually think it's insoluble. It'd be like that white powder precipitate you see being formed. A couple quick things here. In a little practice for the AP exam, in the writing reaction portion, you want to make sure you get rid of spectators. Anything that's soluble or aqueous, we can turn to ions. So in water, it's really sodium ions and chloride ions, silver ions, nitrate ions, sodium ions and nitrate ions, and silver chloride here is insoluble, so it stays together. Basically, sodium and nitrate are eliminated from these reactions because they're spectator ions. So your real reaction is just Ag plus aqueous reacts with Cl minus aqueous to produce silver chloride solid. Okay. Now, once you see that you form this precipitate, precipitates actually are slightly soluble. So we start with the precipitate now, and we use reversible arrows because it's reversible. And it is really mostly favoring the left side, though. But the slightly soluble nature of this would produce a few silver ions and a few chloride ions. So this is what we want to look at when we form precipitates. You form them first, and then you take the precipitate and you make it slightly soluble, reforming those cations and anions that it came from. Now, anytime you have that equilibrium going on there, we can characterize that with an equilibrium constant. In this case, it's called the solubility product, okay, or also called KSP. It's simply the product of the ions in solution. Remember that when you write an equilibrium expression, solids will not appear in them. So let's write the KSP for number 1. So I'm going to go back to 1 here so we can see what we're working with. It's products over reactants, so there's our products. So KSP is equal to Ag plus, in brackets, times chloride, in brackets. That's the concentration of those two things. And because the precipitate is a solid, this is all our KSP is. So equilibrium expression, or KSP, for precipitation reactions is just the ions it came from. Don't forget, this was kind of a unique scenario here. There weren't any coefficients. If there were coefficients, they would become the exponents for each of those things if we needed them. Okay? So got a couple practice problems for you to do here. Why don't you pause and do the first one, then see the answer, and then try the second one, and again, see the answer for that one. So, pause now. Okay, so got to finish off the reaction first, and what we have here is the calcium ion, aqueous, and we also produce the fluoride ion and 2 moles worth. When this thing breaks apart into calcium, fluoride, and there's 2 fluorides, so like this. KSP for this then would look like this. The calcium ion concentration times the fluoride ion concentration to the second power. Okay? Alright, pause, do the next one, see if you can get it, and check when you're done. Okay, so here we have silver being produced, the silver ion, which is aqueous, and so was fluoride up here earlier. And we produce 2 moles worth of this. And we also produce sulfate, 2 minus, and aqueous. KSP for this one will be the silver ion concentration to the second power times sulfate concentration, KSP. So all equilibrium values or constants, they are experimentally determined. So KSP is experimentally determined, and so are those values from the previous chapters, KQ, KA, KB. And here we're going to calculate. So the way we do these problems is going to be a rice table with the precipitation substance dissolving. So we're going to calculate KSP. That's our problem here. We have a lead ion concentration found to be this for the substance lead 2 chloride. So that's your substance you start with, lead 2 chloride. So that's going to be Pb with a +2 charge. Chloride has a -1 charge, so 2 would cross over, and it's PbCl2 like this. So we're going to do a rice table. Okay, when in doubt, rice it out. So anytime you do equilibrium, you need to be doing rice tables. So the products for the reaction here are going to be the lead ion, Pb2+, and 2Cl-. Okay. Now the way these reactions work out is, this is not very soluble, but whatever is soluble will break apart into its 2 ions. So how we do these ones, it's always going to be this for the precipitate, always going to be this. We say S amount is soluble, and whatever is soluble completely dissociates, so you're going to lose all the S amount, and it becomes 0. Okay, so only a small amount here is soluble, you'll lose all of that stuff, and it dissolves. Over here now, it's all about the ratio. So we start off with none of these things, and whatever is soluble, we're going to gain in the ratio, 1 to 2. So we're going to plus S amount and gain 2S amount of this. So it's going to be S and 2S. Now, I personally like to do the whole rice table, but you can see the pattern here. It's always going to be 0 for the amount of this you form, and these two guys are going to be S and 2S in this case because of the equation there. So you technically can skip to these numbers, these variables here, S and 2S, but I think it's helpful to see how it's put together. Now that you have this, we can start to solve for KSP. KSP will be equal to the lead ion concentration times the chloride ion concentration squared. Okay, and we can now plug in the S's there. So we're going to have S in here, and we're going to have 2S in here, and then we square it. So what you end up with then is, I'm going to change this part really quickly just to help us out here. This part right here ends up being 4S squared. So then multiply by S, you end up with 4S cubed. Okay, so we need to know what S is. Well, there's one more piece of information in this problem that's going to help us out here. It says this is the concentration of the lead ion. So that means right here, the lead ion has this value of 1.62 times 10 to the -2 molar. So therefore, if lead is S here, and it's also this concentration, this is the S value. So we can plug it in for S now. So it's going to be 4 times 1.62 times 10 to the -2 cubed. And when you do the math on that, 4 times that cubed, you end up with a value of 1.64 times 10 to the -5th, and that's the value for KSP. K values are unitless. So that's how you find KSP while doing a problem. So a quick little review here. We always start with S amount. Whatever is soluble, you lose completely. And we're going to gain that ratio then S and 2S. You plug into the KSP expression, and you kind of simplify it down to 4S. Now this would be 4S cubed, like this. And then try to figure out what S is by reading through the problem carefully. And plug it in and solve for KSP. So you got another practice problem here. Why don't you maybe try to get the rice table set up, and then pause and see how the answer goes. And then if you need help from there, you can watch more video, or you can try to do it on your own. So pause and good luck. Okay, one quick thing, my pen just broke, so I'm going to have to do this with the mouse, so that's not going to be very good handwriting, so I apologize in advance here. Okay, so we're doing bismuth sulfide, and you'll find out that bismuth It's kind of, I would not expect to know its charge off the top of your head. Uh, in fact, bismuth is actually probably a Roman numeral in its name here, and bismuth is a 3 plus charge. Sulfide is 2 minus because it's underneath oxygen, so it's also 2 minus. So bismuth is going to be Bi 2S3. Okay, got the pen working. Okay, so it's Bi2S3, and it's going to become 2 bismuth ions and 3 sulfide ions. Okay, so remember, whatever is soluble is completely dissociated and will dissolve in that ratio. So it's going to be a plus 2s amount, a plus 3s amount, because the balance equation is that ratio. One of these dissolves into 2 and 3, and end up with 2s and 3s. Okay. Now in this problem here, they tell us the solubility is right there. So this is how much will dissolve moles per liter here. That's actually your S value right here. Okay, so you can say that's S equals that. So that means we can go right into KSP now and plug in. You're going to want to plug in the actual letters here, the variables 2s and 3s. So it's 2s, and then this thing is going to be to the second power, and then it's going to be 3s to the third power. And it might feel like you're doubling up on stuff, but that is what you plug in there when you plug it into the expression here. So when we do those two things separately, you end up with 4s squared, and you end up with 27s cubed. And when you combine that together, you'll end up with 108 s to the fifth power. Okay, so now we can plug in our s value here. So it's 108 times 1.0 times 10 to the negative 15th to the fifth power. And when you do the math on that, you end up with a very small KSP value, which is 1.08 times 10 to the negative 73rd. So it's not uncommon to have KSP values that are absurdly small like that. And typically, the smaller this thing becomes, it does mean that it's not very soluble. Okay? Now we can work backwards. If you know what the value of KSP is, you can work backwards to figure out what the solubility of that compound is. So in this problem, we know what KSP is. We're going to try to calculate solubility. So in this one, you start off with your race table and write your reaction for this. You always have to write the reaction because you do need to know what this thing breaks apart into. Well, if it's copper 2, that means it's got 2 plus, and iodate's minus 1. So it's going to be in the iodate ion, which is 3 of them, or IO3 like this, and there's going to be 2 of them. That goes ahead and dissolves into 1 copper ion and 2 iodate ions. So we have S. We're going to lose all of what is soluble, and it's going to produce the ratio of 1 to 2, so it's plus S plus 2S, and you get this. Okay, so now we set up KSP, and we know what its value is, so it's 1.4 times 10 to the negative 7th, and it's going to equal the products. So it's 1 of these and 2 of those, so it's going to be S to the first power times 2S to the second power. And when we kind of simplify the right hand side here, we end up with 4s cubed. Okay, so our goal now is to basically, these two are equal to each other here. Our goal is to solve for s, so we're going to divide this by 4, which gets rid of the 4, and then we're going to take the cube root of that particular quotient. Okay, and when you do that with 2 sig figs, you should end up with a solubility of 0.0033, and the unit for solubility is moles per liter, or molarity. Okay, so that's how soluble this substance is. So if you know what KSP is, you can work backwards to find solubility. So that's the big relationship between those two things. Now, once you know KSP values, you can compare them. Okay, we can compare KSP values to see how soluble something is. But you can only compare KSP values directly if the salts have the same ion-to-ion ratio. If salts don't have the same ion-to-ion ratio, then you actually have to calculate the solubility. Okay, so here's kind of what we mean. I have 2 practice problems here. We'll do one in class and one together. So let's do one together here. All of these ions that you're looking at here dissolve in a 1-to-1 ratio. Okay, so in your notes you can say that. All 1-to-1 ratio. So if you break these all in half, you have one barium, one carbonate, one barium, one chromate, one barium, one oxalate. All of these are dissolving in a 1-to-1 ratio, and when that's the case, you can look at their KSP values and say which one is the most soluble. Okay. Remember the value of K. The higher the value of K becomes, that means it favors more product. And in our case here, more product means favoring more ions. Okay, so this is the most soluble because its KSP value is the largest. Okay, and if they're all 1-to-1 ratio, I mean, I'm not going to solve all of them here, but basically, if it's a 1-to-1 ratio, that means it's going to be the first substance, barium, its concentration, to the second substance, oxalate there, so S. So you end up with basically S squared. And when you solve for S, the biggest KSP here in this scenario will give you the largest solubility, the largest S value. So again, anytime they all have the same dissolving ratio, it doesn't have to be 1-to-1, they could be 2-to-1, they could all be 3-to-1, or some other combination. As long as they have the same ion ratio when they dissolve, you pick the KSP as the largest, that's going to be the most soluble. Now we'll pick up in class with practice problem number 11. If you want to give it a try, you're more than welcome to, but we'll do this one in class. All right, good job.